Okay, so here's where we were. We spent a bunch of time talking about, whoops, wrong button. We spent a bunch of time talking about this picture and how even though we measure the quantity on the left as happening on the boundary, it is really very much actually happening in the middle. It is really, even though it's an algebraic expression, I want you to think of it as a thing, a stuff, a kind of almost visceral stuff that accumulates over the interior. It happens in and accumulates over the interior. And then ditto with flux. It is just a matter of it being measured on the boundary. That's the illusion. It is actually an accumulating quantity that you can see where specifically it's happening. And quantify that with divergence. It is happening in and accumulating over the interior. Okay. All right, so that pitch having been made, let's go back over to here. And we've got this stuff, right? That's accumulating over the interior. And looking at these equations, I mean, if flux is a triple integral of divergence, then that means that I can think of a differential amount of flux as being divergence times a differential amount of V. And noting how similar that little thing is to this familiar old equation, dm equals density dV, notice that divergence is playing a role. It's a density, right? And we've talked about different kinds of density before, right? I prepped you all in terms of, well, we have population density, and we have mass per unit area and mass per unit length, and in general, stuff per unit size is how you should think of a density, right? Well, we're seeing here a new kind of a density. The stuff is flux. So, and again, I made the case that flux is a lot like mass. It's a kind of a stuff, and it accumulates in the same way mass does, and it happens in particular locations. And, well, it has a density. So, in the same way that what we routinely call density is mass per unit volume, divergence, likewise, is flux per unit volume. And so the term that we use to describe divergence, very common, by the way, extremely common, is that it is flux density. Because of that connection. So this is, you'll hear this term a lot going forward. I mean, sometimes people will describe the Gauss's divergence theorem as a statement about flux density. People will say, I mean, routinely, hear the following language. Flux is a triple integral of flux density. Right? Which, using this shorthand, it is. Flux is a triple integral of flux density. Okay. But I love this terminology. It is very sort of physically suggestive. It's a good way to think about divergence. Right? And so anyway, I encourage its use, and certainly I wanted to make sure y'all were prepared for seeing it. Now, just along those lines, and partly as a tool for digesting what we just talked about, let me point out you can do the same thing with the fundamental theorem of calculus. So here's fundamental theorem of calculus as you're accustomed to seeing it. Let me rewrite the left-hand side. I want to give it a name and a symbol so we can talk about it as a kind of a stuff. But we made a big deal before the break about how f of b minus f of a represents change. Change accumulates. We measure on the boundary, but it's actually literally happening in the interior, and it's the accumulation of how this expression adds up over the interior that actually makes this work. And so this stuff, this thing, called change, and I'm just using delta just as a way of representing change. It's just notation. Change is an accumulation of stuff Therefore, d-change, a differential amount of change, is f prime dx, and therefore f prime is, per unit length, of course, f prime is change density. You could. This is a new interpretation that you can think of for a derivative, and I know you've got plenty of other interpretations for the derivative, right? It's not like you're short. You don't have a shortage of interpretations of the derivative. But I think this is a big one. It's a really good one. Yes, derivative is the slope of a graph. Fine. Yes, derivative represents velocity. Your position on the road as you're driving as a function of time. Very importantly in this context, derivative is change density. And I want to encourage you all to think of it in those terms. Here we go. Change density. Okay. We can do the same thing with Green's theorem. Here's Green's theorem. And recall, Green's theorem computes these boundary line integrals. I want to talk about how to think about boundary line integrals a little bit. What does a line integral compute? And this is just a quick reminder. I'm going to give myself a little space to work here. Line integrals, we have different interpretations, but one of them was given a curve. A line integral measures to what extent the vector field is flowing along the curve. Right, so the line integral along in here, you're going to get a positive amount of line integral because, well, this fluid represented by the green vector field, this fluid is to some extent, about like that anyway, to some extent is flowing along the curve. Now, on this next little chunk of curve, you're going to get very little, actually even further than that, I drew this. On this next little chunk of curve, you're not getting any flow along the curve, you're getting flow perpendicular to the curve, and the line integral doesn't measure that. This is not the kind of thing that line integrals measure, right? So there's no sort of fluid flow along the curve there. But then lastly, over here we have, in fact, if we're going to the right, my intention is this curve is oriented to the right, then here the fluid is actually flowing backwards along the curve. Right? So if you think in terms of, if you think of line integral as measuring, remember we had this point of view, the extent to which the fluid is flowing along the total curve, then we can take a new interpretation of this integrand here, this expression here. This is line integral. How much is the fluid flowing along a curve, but specifically where that curve is a boundary. And now let me draw a picture of what that looks like. A boundary, right, here's a solid two-dimensional region. Boundary is, like this. And now let me try to draw a picture of what is it that this is measuring, this line integral around the boundary. Well, okay, it's measuring how much is the fluid flowing along this curve. Okay, but wait a second. To the extent the fluid is flowing along the curve, well, the curve is going around a kind of a circle. Right? The curve is making a full 360 counterclockwise turn. Right? So if the fluid is in fact flowing along the curve, to whatever extent the fluid is flowing along the curve, we're talking about a fluid that's doing something kind of like this. It's like the fluid itself that the vector field represents. The fluid is kind of circulating. You understand what I'm talking about? Like there's a little whirlpool in the bottom of the bathtub, that kind of thing. So, no surprise, the term that we use to represent this is circulation. So anyway, this is just a physical way to think about, what Green's theorem is computing. I think it's kind of appealing to have a way to think, a physical or geometric way to think about what the object on the left is. So anyway, with that in mind, thinking of Green's theorem as computing circulation, notice that Green's theorem here effectively is telling me that, and compare, as usual, think about how mass accumulates over a two-dimensional region. Let me do this in red. How mass accumulates over a two-dimensional region. dm is density dA. And we have, again, a new notion of density. I can think of Green's operator as being kind of a density. Green's operator is telling you, look, we've got this grand total. We've got a circulation that's accumulating over the interior of this two-dimensional region. Green's operator is kind of telling you how much of that circulation is actually happening, per unit area, of course, in a general vicinity in that interior. So Green's operator is a density. It's not mass density, of course, right? Mass density is mass density. This is a density where we're computing circulation instead of mass. And so the term that we use for Green's operator here is circulation density. And another common term for this is vorticity. Yeah. How we doing? Is everybody happy? All right. So, nice points of view. Okay. Moving along. So I want to talk about some more applications to, some physics points of view on things. This you might call an actual application to physics. And I remind you, I'm going to zoom in here, that we can think of mass as a triple integral of density. Old news. Now, for reasons that will become clear in a moment, let me take a derivative with respect to t of that equation on both sides and multiply by a minus sign. Humor me, right? So that's what you get if you take that top equation and do as I described. And let's see here. I need to do that. Then let's think about what is dm dt. What is dm dt? What's more specifically negative dm dt? If m represents how much mass you have inside of a solid region, dm dt would say how fast is the amount of mass increasing. Negative dm dt would then suggest how fast is the amount of mass decreasing. Oh, well, hey, wait a second. How fast is the mass decreasing? Let's go over to this picture here. Let's suppose that my vector field looks like this. My vector field is kind of, going outward, if you will, kind of from a solid region like that. What is flux? Flux says how much fluid, how much mass of the fluid is actually leaving your region. Flux is negative dm dt. Right. So, having rewritten our sort of mass density equation in this form and equating these things suggests a nice point of view. Oh, let me use a better consistent color choice. A nice point of view on divergence. In this context where we've decided we've got a certain amount of mass that's in this region, and I want the vector field to be thought of as how that mass is sort of flowing around. Maybe the mass isn't. Let's not think of it as a solid. Let's think of it as a liquid or a gas or something like that. Gas is kind of convenient. We've got this mass kind of flowing around and kind of flowing outward. So there's a certain amount of mass leaving our region. The flux tells you that. And so in this situation, what is divergence? It's just you interpret straight from the equation. Divergence tells you how fast the density, the mass density, is decreasing. So I like to call this local decompression rate. right? How fast is the mass density going down? So, when there is a bunch of mass leaving, sure, I suppose in some sense you might insist that, well, the mass that's leaving has to be mass that was right next to the edge, right? But there's different ways that you can accomplish that. You could have all of this mass in here not moving, just sitting there, and have this mass here be what's actually moving out. Or it could even more simply be that all of this mass is all at the same time radially moving outward. Right? Now let's consider this scenario. If the mass, all of the mass except for maybe what's in the middle there, if it's all radially moving outward, right here at the edge, yeah, sure, there's mass moving outward, but there's also mass from here moving in toward it. So at that point, the density would not be changing. And at that point, the density would not be changing. Right here, though, the density is taking a big hit because that mass is leaving, but there's nothing going in toward it. So my point here is that just because there's a bunch of mass leaving, that alone, just that there is flux, tells you only about how the total amount of mass is changing. If you want to know where is that mass really coming from, where are we losing mass on the inside? Divergence, not flux, divergence tells you where, as a function of position, the density is actually decreasing. All right. So that's one interpretation of divergence. Now, here's a different point of view you could take. And this is common also, right? I was thinking here about a kind of a stuff, a kind of a mass where the density is not constant. Gases have this feature. The density of a gas changes, depends a lot on pressure and temperature and the stuff like that, right? Altitude, right? You go up in the mountains, the air is not as dense up there, which you will definitely feel. But let's think instead of a fluid where the density is constant. Now, this is a different scenario, right? We're going to have a different kind of a picture. Let's think about, for example, liquid, and more specifically, let's think about water. Water has pretty constant density. It's very surprising because, you dive down to the bottom of the swimming pool and you get, oh man, the ears, right? Oh wow, it really hurts. There's a tremendous amount of pressure down there. The pressure is coming from all the water that's above you, pushing down and then subsequently in your ears, right? That's not the same as density. If you go to the bottom of the swimming pool, the actual mass per unit volume at the bottom of the swimming pool is almost exactly the same as it is at the top of the swimming pool. And I don't know the exact numbers, but it does not vary all that dramatically even when you go like deep in the ocean. It's pretty constant. Okay. So, we would have to take a pretty different interpretation then of, let's see, where's my picture? We'd have to take a pretty different interpretation of this picture. What might this mean? Oops. What would this picture mean if this was water, and there was water flowing radially, uniformly away from some central point? What would that mean? Actually, golly, I don't think that's even possible. Right? Water can't do this. Right? Water in the actual physical situation. If the density is constant, all this water is flowing out of that region. Is water going to just magically be flowing into that region from nothingness? Or where's the water coming from? You see the problem? So, let's take an algebraic point of view on this. Here's a different way to think about mass as related to density. Mass is triple integral of density. Density is mass per unit volume. Take a time derivative of both sides. You get this. And from a point of view of, thinking about this as representing water, if we think of this as representing water, the flux through the boundary there, that tells you how much mass per unit time of water is leaving. Well, if the density's got to be constant, then there must be a water source somehow. I don't know how it's getting in there, but something's generating water. That's because how else could water be uniformly flowing out of this region? So there must be a source in there somewhere. So again, you look at this equation as written here, compared to Gauss's divergence theorem. Flux represents the rate of change of, the rate that mass is flowing out of the region. Therefore, flux represents the rate that new mass must be being introduced into that region. And those being equal suggests another interpretation, different interpretation, in this different physical sort of scenario, different interpretation of divergence. That mass is somehow or another is detecting how much of a mass source is there. How much mass per unit time? Mass per unit time says how much of source of mass do you have is happening, and then of course it is per unit volume. So it's a density. So you can think of divergence as being source density. Right, so grand total, there's got to be over that entire region, the mass is coming from somewhere. Something's generating water. Well, how much of that water is coming from where? Divergence tells you. So different interpretation. So which of these interpretations should you use, or should you use a combination of these? It depends on your physical scenario and the kind of fluid that you're dealing with. And we're not going to, pull on that thread and go down that direction. But I wanted to point out, and I want you to have a basic understanding of the idea that, look, divergence this is a very natural idea to relate to fluids and how fluids flow. Fluids, liquid fluids, gas fluids, anything where there's a flowing of stuff, divergence, very natural. Natural interpretations. Okay, all right, moving along. Next physics interpretation involves gravity. So, hope you all might remember a little bit of gravity stuff from when I was in high school. We had a class in 9th grade, I think it was, called physical science. Do they still do something like that? And y'all have seen the inverse square law of gravity, I hope. If you haven't, I hope you have some familiarity with gravity. We all walk around inside of it. We deal with its consequences increasingly. And here's the formula. The force of gravity is, it depends on the two masses, and then there's Newton's gravitational constant, but importantly, it's inversely proportional to distance squared. Okay. All right. So this is again, this is very high school kind of a formula. After all, forces are vectors. That's not a vector. That's a scalar. This is again the high school point of view. They haven't introduced vectors, and so they can't really write down what is the actual vector representing the force of gravity. Worse, they can't represent the vector field that is gravity, the gravitational vector field. So let me get rid of that. Here it is. This is a formula for the gravitational field. Really, I suppose I should call this gravitational acceleration, because this is what you multiply times m2 to get the actual force. So this, what I've got written down here as F sub g is really the acceleration field. But anyway, we're going to call this F, I suppose, for field. This is the gravitational field created by, let's say, the mass of the Earth. Or more to the point, let's talk about a single point mass. Right? And this is what the above formula turns into. Now this looks like a typo. I know you're all looking at this cube right here and saying, hey, that's not inverse square, that's inverse cubed. But let me rewrite this formula a little bit to persuade you that this is in fact inverse square. Negative g m1 over magnitude of x squared times x over the magnitude of x. Point being that this is actually just a great big unit vector. Right, so in terms of magnitude, yeah, the magnitude is inverse square. This extra copy of magnitude of x is just part of this unit vector that describes the direction. Everybody good? All right. Okay, so turns out, and this is a calculation that you can all do on your own. In fact, this is a calculation that you all should have already done. You may remember back in section 5 whichever the section is on vector fields. One of the things that you did with vector fields is you computed a bunch of constructions that we didn't know what they meant at the time. One of them was divergence. I don't know if y'all remember. Anyway, flip back to the section on vector fields and look in the exercises, and you'll notice you've already computed Green's operator for some vector fields, and you've already computed divergence for some vector fields, and one of them was this with a different constant. I think I called it k instead of gm1. But morally, it was that. And so you crank out that divergence, and the divergence, amazingly, is 0. This is a really weird fact about gravitational fields. Divergence is 0. This is a really important fact about gravitational fields. Now, of course, disclaimer, when x is 0, there's this huge explosion, right? And this vector field isn't even defined when x is equal to 0. So we can't talk about what the divergence is at x equals 0, right? But everywhere else, the divergence is 0. Okay. All right. So here's some powerful consequences of this. It's really surprising how this works. So let me start off with this question here. We're going to have an object, massive object M, that's sitting outside of a region R. Right, so here's our picture. Here's that mass M. That mass creates a gravitational field. That gravitational field is stronger when you're near the mass, and it's weaker when you're far from the mass. But worse than that, this gravitational field is changing the direction that it's pointing. It's always pointing toward the mass. And so this is not a really simple gravitational field. Now I want to ask the question, let's talk about the flux of this gravitational field through the boundary of R. R is R is this region here, the solid region. And I want to talk about the flux through the boundary curve, the boundary surface, boundary surface there. And what a hard problem this appears to be. I mean, I got to parameterize that surface. It's all lumpy and bumpy, right? And the vector field is different directions, different magnitudes. Look at even algebraically, look at the formula for it. It's got a square root cubed in the formula. This looks like a really ugly calculation. Yeah, anybody sees? So the flux of that gravitational field of that, even if it's just a single particle, the flux of that gravitational field through this boundary surface looks like a really hard calculation. But it's not. It's a really easy calculation, as it turns out, because after all, flux is a triple integral of divergence. Divergence is 0. And therefore we have 0. Isn't that nice? Hey, we just saved ourselves a tremendous amount of pain by capitalizing on the fact that the divergence is 0 away from where the mass is, and knowing Gauss's divergence theorem. All right, now, very importantly, where the mass actually is. Right, at this point, where the mass actually is, not only is the divergence not 0 here, but the divergence isn't even defined at this point. And so it's very important that the point be way over here outside of the region, because when I cited Gauss's divergence theorem happens over here. We've got this green solid, this blue boundary surface, and I need, for where I'm applying Gauss's divergence theorem, I need for everything to be well-defined and continuous. Otherwise, Gauss's divergence theorem is not true. It doesn't apply. So, thankfully, the discontinuity way over here. So, next question I want to consider, though, is what if it's not? What if we actually have the discontinuity is, where we are in the solid that I'm interested in? What if the mass is inside the region R, as we see over here in this picture? Right now, our mass is there. Our region R is like that. I cannot cite Gauss's divergence theorem on this solid region R because there's a discontinuity in the vector field. So that's too bad. So here's the slick move. What we're going to do is we're going to say, sure, there's mass there inside of R, but let's look instead at R naught. This is a really clever move, by the way. Wish I thought of this. Somebody beat me to this by probably at least 100 years. So let's think about that little region, R naught. Right, so I've hollowed out a little cavity around the problem area. Now, R naught is a different solid. The discontinuity is not at all part of R naught. I can perfectly safely apply Gauss's divergence theorem to R naught. And let's think about what is the boundary of R naught? The boundary of R naught is we've got this surface here, which is the boundary of R, right? But then we also have, as part of the boundary of R naught, we have that surface. Now, away from the solid is what you're going to want to call inward there, which is fine. So the boundary of R naught is boundary of R, but then inward oriented S, or I'm going to say minus S. S is oriented outward. So boundary of R minus S. So here's Gauss's divergence theorem applied to this region R naught. Oh, yeah. Sorry, to the region R naught. Gauss's divergence theorem on R naught gives us this. The boundary is boundary of R minus S. The divergence is 0. So this triple integral gives me 0, and a punchline is we don't get the computation that we wanted, right? We did not, as a result of this, get to conclude what that is. All we've shown is that this difference is 0. So said differently, what I've shown is not that I can compute this boundary flux, but that this boundary flux is equal to this other flux. And this is disappointing. It's not what we were hoping for, right? But nevertheless, there is some pretty good value in this, as it turns out. Knowing that this boundary flux is equal to this sphere flux. Nice punchline. This sphere could be anywhere. Let me go back to the picture. Looking at this picture, and let me zoom in. I was considering, recall, that there's a little mass right there, and then I drew a sphere around it. And I made the observation that the flux on the boundary of R is equal to the flux that we're seeing of that mass through that sphere. Well, let's suppose, hypothetically, what would we have done had the mass been up there? Well, if the mass had been up here, I would have drawn the little sphere up here, and I would have hollowed out that region. Same calculation. We get the same answer, right? And whether this mass is up there, or down here, or over there, or up here, or over there, or over here, where it is doesn't change how this mass is going to create a gravitational field, and on this sphere that I carefully arranged in exactly the same way, on that sphere I'll always get the same value because I'm always drawing the same picture. So the nice punchline that we get here is that when the mass is inside of the region, I don't know what the flux is, but I do know that where the mass is doesn't matter. The mass could be anywhere inside of the region. All that matters is how much mass, not where the mass is. Cool? All right. Okay, this is going to be a surprisingly important thing. Okay. All right, so now I want to consider yet another problem. This one's really going to seem scary, but it goes down pretty smooth. So let's suppose that we have a cloud of mass. I guess we'll use yellow here. So non-constant density. So I'm trying to represent here that there's a high density of mass over there, low density of mass over here, another little hot spot of mass over here, mass distributed everywhere. Scary. Let's contemplate a really hard problem. What's the total gravitational field created by all of this mass? The mind reels because, oh my God, in order to do this, look, that little particle right there, that one little particle creates a little gravitational field that's, inverse square radial. But so does this little piece of mass, and so does that little piece of mass, and that little piece of mass, and that little piece of mass, and this, and I guess there's probably a little piece of mass over there somewhere, and there's countless little pieces of mass, each one of which creates its own not very nice gravitational field. The total gravitational field I would have to add up all, oh my God, right? And this is horrifying to contemplate how ugly that gravitational field would be to write down. Now here's an even harder question. Let's compute the divergence of that horrifying gravitational field. Well, come on, surely you jest, right? How could we possibly, I can't even write down the gravitational field, could we possibly compute the divergence? And it's going to turn out that, we're going to be able to compute the divergence pretty quickly by some really clever observations. So here's how this breaks down. First observation to make, and by the way, we're going to consider, I'm going to try to compute the divergence at, let's say, that point right there. First observation, if I were to draw a little ball around that point, and if I were to think about the flux through that boundary surface, and I know we're not trying to compute flux, we're trying to compute divergence. Right? But just work with me here. I want to compute the flux. You'll see why momentarily. I'm going to compute the flux through that boundary surface, through that boundary sphere. Well, our first result up here says that the mass that's outside of that sphere contributes 0 to that flux. Right? So as far as this flux calculation goes, I get to ignore all except for the mass on the inside. So all of this, I get to throw away. I don't have to think about those pieces of mass. I don't have to think about those or those. All of this, all the mass outside of my region doesn't affect the flux. Because again, our easy starter example, Gauss's divergence theorem tells us I get to ignore all that mass. Next observation, and this is just, I appeal to your sense of how the world works. Density tends to be generally approximately continuous. So density, it might be higher here and lower there, but it's going to vary in a sort of a continuous manner. And so if this little ball that I'm looking at is sufficiently small, then the density in there is approximately constant. Okay, so here's my actual, where I'm sitting then. If I want to compute that flux, the flux, sorry, I got ahead of myself. Last observation I want to make about this region, I get to put the mass wherever I want to. So I'm going to take all that mass that was distributed uniformly through there, and I'm going to squeeze it all down to the center, because after all, it doesn't matter where the mass is, right? We've already argued that as you're interested in flux around a boundary surface, the mass could be anywhere, it doesn't matter. So I'm going to squeeze all the mass down to a single point. Now, this problem is looking a lot more tractable at this point, right? We used to have this horrifying distribution of masses everywhere, and now I have just one point of mass at the center of the sphere. Okay. And I'm sorry, I'm looking at the clock and realizing I'm out of time, so I'm going to have to finish this up next time. But I'd like to point out, we've already made tremendous strides toward this mind-reelingly intimidating question. And now it's just a matter of writing down some details and celebrating at the end. Okay. All right. We'll do that celebration next time. See y'all later.